So the first thing that I talk about whenever I talk about the physics of music is I talk about waves. All right, and I always bring the my snaky spring. All right, and I need someone to hold the other end of my snaky spring. All right, Russ, and you look strong and like you can handle this today.
All right.
All right. So your job for now is just to hold it.
All right.
Okay. So what I'd like to do is, I'd like us to envision that this snaky spring was infinitely long, and that Russ was infinitely far away from us. Which,
Oh, simple.
Some of us might like that idea. Some of us, I personally, I don't want Russ to be infinitely away from me, but because there is a problem with using a finite medium for carrying a wave, because I want to demonstrate what the simplest wave is, and the simplest wave that I can think of is a single pulse. Okay, but the problem with that wave is that it reflects off of Russ's hands, and it comes back at me, right? But if we can just sort of envision the part of the wave that starts from where I make the disturbance and then propagates down, and ignore right before it, everything after it hits Russ's hand, then we'll just talk about that outgoing pulse, the outgoing pulse from my hand. So the real question is, what is a wave? What makes a wave, right? Because I would consider this to be a wave, right? But that would not necessarily be what you would think of as a wave if I were to just say, okay, imagine a wave. You probably wouldn't think of that. So what is it about that makes it the most simplest wave? What is a wave? I know you guys didn't do any reading beforehand, so
no.
You don't have to even, I don't expect you to know. It's just, what do you think of as a wave when you think of waves?
Like terms?
Like terms, yeah, anything.
Frequency?
Frequency, okay.
Amplitude?
Amplitude, okay.
Those were made to.
Wavelength, okay. Wavelength, okay. All right. So now, I think we would agree. Speed, okay. We got wave speed, wavelength, amplitude, frequency. All right. Now, I think we would all agree that this wave had an amplitude, right?
Yeah.
And I could probably change that amplitude to be whatever I wanted it to be, right? Okay. And clearly, it has a speed, right? We could pull out our stopwatches and we could time how long it takes to go down there and how far away we are from each other. And we could figure out what the speed is, right? And it turns out it is important for us to consider wave speed, and it turns out here's your first sort of rule for physics of music, is that the wave speed depends on properties of the medium, okay? So if you change a property of whatever the medium is through which the wave is propagating, you're going to change the wave speed. That may become important depending on what the medium is that you're trying to put a wave through. If we're trying to set up a wave in air, we can change the wave speed by changing the temperature of the air. That's the most sensitive thing that the wave speed is sensitive to in air. Or you could change the property of you can change the mixture of the gas itself.
Pressure.
So you could go from, not so much pressure, but what's actually the air is made up of. So you could go from the typical atmospheric conditions where we have 75% nitrogen and almost 25% oxygen and some other trace elements, and you can go get rid of most of that and bring in almost all helium, and you'd have a lot different wave speed. And if you inhaled that, your voice sounds different because you've changed the wave speed without changing anything else. But typically for most instruments that use air as a vibrating component, we're not going to change the wave speed, but we will change the wave speed of stringed instruments. But that doesn't really answer the question of what is a wave, right? Because if you look at our simple pulse, and remember, we're only looking at the part of the pulse going from my hand to right before it hits Russ's hand. I think if we look carefully, we would agree that there is no defined frequency for that, and there's no defined wavelength for that. So those terms alone, even though they help us understand the waves that we're used to envisioning, they aren't appropriate for this simplest type of wave. All right. So what makes a wave is that it carries energy through a medium without disturbing the medium itself. Okay. Now we can show that it's carrying energy if we look at Russ's hand, right? Because as the wave hits Russ's hands move, right? Okay, now Russ, to me, looks like a relatively strong guy, right? If I didn't know Russ, I probably wouldn't necessarily want to run into him in a dark alley. He has that friendly look, but he looks like he could be trouble if he wanted to be, right? I mean, you know. So,
What do you mean? I could be trouble.
Did you eat your Wheaties this morning?
No.
No? Are you feeling a little strong?
Oh yeah,
You
sure.
are? Okay, can you hold it still, please?
I will try.
So that it
yes.
doesn't move? You got it?
Yeah, I got it.
Okay. That wasn't very still. Right? There's a lot of energy being sent down, right? And you won't be able to hold it still because that energy is being translated into your arm. But the point is that this, this part of the spring here doesn't go down and hit your hand. It's
right.
the part that's hitting.
Right.
It's the energy that's being propagated. Just like when I'm speaking, I am creating sound waves, right? The sound waves are traveling through the air. But the air that my vocal tract is disturbing to cause those sound waves, those air molecules aren't hitting you guys, and aren't hitting your eardrums, they aren't hitting your nose either, so you're not smelling my breath every time you hear me, right? The air is, the sound waves are propagating through the air, but the air is not moving very much, right? So that's the essence of a wave. A wave is something that causes a disturbance in the medium that carries energy but doesn't actually carry the medium along with it. All right, so now if I were to take our medium here, this snaky spring, and send not one pulse down, but start sending lots of pulses down, and then if I figured out just the right rate at which to send those pulses, I could get the reflected pulses to combine with the outgoing pulses at just the right rate so that it looked like we had a wave that was not traveling the length of this, but that was taking up the whole essence of this spring and was just standing there. All right? So we call this type of motion, we call this a standing wave. And the resonances that are musically important are often standing waves. So if you're going to use some sort of air column, like a pipe or a tube, to resonate in your instrument, like if it's a wind instrument or certain types of percussion instruments that we can talk about, you would have a standing wave of air, right? Air pressure, really. But if you were trying to use a string instrument, then you would be interested in the motions of the string. So this looks a lot like a vibrating string, and this would be one resonance. This would be the lowest resonance of a string. Now if I send the pulses down faster at a higher rate, first I get a little bit of garbage, but then I can find the right frequency at which to send the wave down, and I get another standing wave. And this is in fact the second resonance, and it's one full wavelength. So this is what kind of has that sinusoidal motion that you're more familiar with when you think of a wave, and this would be the second resonance of a string, or a second resonance of something that an open pipe. We'll talk about in a little bit. And then I can go to higher and higher frequencies. Oops. If I can find them. I think that has three loops. Three loops, and then we can go, and we can get 4 loops usually. And so on and so forth. And if we were careful, now you'll notice that I'm going to go back down to a lower one. There's our lowest one again. Now with these standing waves, you'll note that we have not only a well-defined frequency, that is, we can tell how many oscillations we have in a single second, well, or over a period of time, because the oscillation is probably taking slightly more than a second. But also we can define a wavelength. For this particular standing wave, we actually have half of a wavelength. All right? And I want to show you guys some tricks to calculate wavelengths for things that are important. All right?